Thanks, Vera. Yeah, so what are PRBLMS? It's actually pronounced problems, and it was a really popular musical track last summer by this artist. How do you think you pronounce this artist's name? I'll give you a hint. It's not 6-lack. But what do you think a voice interface is going to do when you try to pronounce this to it? And so, actually, the artist himself, says that it is pronounced black. And so, again, when you try to pronounce this to a voice interface, it might not do what you expect. And so, specifically in our context, we're talking about a prototype system we've made as a voice interface to Spotify on a mobile app. And so if you say, play black to a voice interface, it might play you something like Black Bear, which is a completely unrelated artist. But in fact, if you say, play 6-lack, it will actually return the artist you're looking for. And that's not really great. In fact, if you go to Black's Twitter account, he actually says, if y'all catch anybody pronouncing it 6-lack or 6-black, enlighten them. So I guess what I'm here to do is kind of show a path of enlightenment to our voice interface and also to multiple voice interfaces and kind of show where they're not doing really well and how we can fix that. Because this isn't really a small problem. You know, Black isn't a niche artist. He's one of the most popular artists in the world. And this also affects a good portion of other content. And it only really gets harder. Black is a pretty simple example. Let's take a look at a track like Navuzi Metro hashtag part 2. So if you say that, you can see on the right what transcription pops out. It says Naboo see Metro hashtag part 2. And it turns out Naboo is a planet from Star Wars, and it's not a musical track. So of course, it doesn't find the track you're looking for. And what about other songs like Pentagrammophone Valhalla? How would you even ask a voice interface to start to form these different symbols? How can it equate the letters that we understand are behind those with the actual name of the song and find it correctly? And right now, it can't really do that. And this is further complicated by the fact that, especially in our prototype, you know, we're using a third-party voice API. You'd almost have to be crazy to kind of roll your own ASR at this point. But these systems are black boxes. You can't always add training data. You can't always add acoustic models. So how can we even begin to detect content that's inaccessible through these voice interfaces if we don't have access to the model to do that? And so what we came up with is basically the idea that when you're running the same kind of program on multiple platforms across different modalities, you can kind of leverage the engagement stats against each other to discover what's going wrong. And so to start with a couple definitions so we're all speaking the same language here, when I'm talking about anomalous content, I mean something that is super popular on desktop or mobile where you can directly click the song, but something that's very unpopular on voice. And so this disparity kind of indicates that there's probably a problem on the voice interface that it can't find it for some reason. When I talk about a voice find, I'm talking about a tracker artist being returned from a voice query. So I ask for Cardi B, the voice interface returns Cardi B. That's a voice find. And then a stream is simply a play from any modality. So let's look at what the content space kind of looks like to see, okay, how can we even begin to detect these anomalies with those ideas we just talked about? And so on the x-axis here, we have the track popularity rank. On the y-axis, we have the total number of voice finds a track has experienced. All these dots are tracks. Which ones are the outliers? It's not exactly clear here. And so we're actually going to create a metric here where we take the number of streams a track has experienced, we divide it by the number of voice finds it has, and this should start to expose some of the tracks that are having issues on voice interfaces. And that's what we see. We start to see these tracks sort of pop out, and a lot of them, you know, have issues like they're using symbols or something like that that voice interfaces don't deal well with. But if you look at this from the y-axis, it's still a power law distribution. And using standard anomaly detection techniques on power law distributions doesn't really work very well. So we're going to log normalize this space. We're going to take the logarithm of the streams and the voice finds to create a more normal distribution from the y-axis. So now we see that we've got a pretty normal distribution from the y-axis, and all these tracks that are starting to emerge at the top are actually problematic tracks for voice interfaces. And so we verify this later. We'll talk about the crowdsourcing approach to that. But this simple detection technique turns out about 80% of those are actual anomalies where the voice interface cannot surface the track properly. So let's use that kind of lens where we can detect these anomalies and see what's going wrong to actually look at how voice interfaces deal with different genres differently. And so what we're going to do is we're going to take the top 5,000 tracks by popularity, and then we're going to run the anomaly detection we just talked about over those top 5,000 tracks. We're going to compare those two populations. We can basically hypothesize that if the anomalous tracks are randomly distributed, that means the voice interface is treating everything pretty fairly. And so an example of a normal genre would be something like pop, where we see it as a distribution among the normal tracks, and it's actually underrepresented among the anomalous tracks. It uses language that voice interfaces can understand very easily, and so it doesn't have a lot of issues. But a genre that voice interfaces disadvantage is something like hip-hop. We see it as a distribution among the normal tracks, but then is proportionally overrepresented among the anomalous tracks. And so a list of all the genres is here, but what I want to kind of key in on, and the two genres that were significantly different among all of these were hip-hop and country. And so there's a lot of research that indicates that both of these genres have unique and specific social-linguistic practices that maybe some of these other genres don't have. And this really seems to push the bounds of what voice interfaces are comfortable transcribing and dealing with. And so that seems to be the reason that these two genres are overrepresented among the anomalous tracks. But let's dive in even a little further and look at the different exact problems that we're having here. So what are the content classes that we're having issues with? And so we're going to look at the anomalies that we detected among the top 5,000 tracks again. And the process of doing this is one of the researchers went through, coded everything by their lexical characteristics, and then both researchers sat down, co-annotated them together, refined the content scheme. And this resulted in 12 disadvantaged content classes. So we're going to talk about them by popularity here, and the most frequent one that occurred was that of English dialects. So for example, if you play a song like You to Baddest, it actually gets transcribed as YouTube baddest, which isn't very accurate here. Expressive and alternative spellings were another issue for voice interfaces. So a popular song last summer also was called Hunt It Racks. And the artist chose to be really expressive and creative and cool in how they named the track, where they use 100 as the number rather than actual letters to spell out Hunt It. But of course, if you say that to a voice interface, it has no idea that 100 IT is equivalent to HUNNIT, and so it often can't find the correct information. Excuse me, I need some water. Another big issue was non-English languages. So asking for dile que tu me quieres actually gets transcribed as delicate Tony curious, which is like pretty funny. And in fact, like a lot of the transcriptions you see from these different problems are just like, they're crazy. And so the problem here is essentially that a lot of these third-party APIs, you have to specify a single language. It can't detect it on the fly, and you can't specify multiple ones, and they'll struggle with it that way. And so when you try to turn it into English because you told the ASR to expect English, you get wild results like this. And so the full list is here and in the paper, and I'd encourage you to check that out. But essentially what I want you to note is there's a really wide variety here. There are a lot of different problems that these voice interfaces are having, and that brings up a pretty big issue when you're tackling these. So should we tackle all the different problems individually? Should we build a dedicated model to translate between English and English dialects? Should we change symbols to their orthographic equivalents, like pentagrammophone earlier? Should we correlate homophones together to make sure the voice interface can surface the right content? This is really time intensive, first of all, to build all these models. Second of all, it's really fragile. Who knows when somebody's going to start coming up with a new way to do things and going to create a new category in our ontology. We don't want to have to redo this every time something changes. So what would a general solution look like to dealing with these problems when you don't have access to the model? And so a brief overview, I'm going to walk you through this, don't worry, I know it's kind of scary. But the top left, essentially, we do the anomaly detection like I talked about. We send these anomalous tracks off to Crowdflower where we have a lot of people pronounce them. And then we transcribe those pronunciations and choose the best one down here. And then we tag the tracks with the best transcription in the system so that we can finally surface the correct content. So let's go through that a little bit slower. So like we talked about in the beginning, we have this algorithm, this process that we found to discover what tracks are anomalous, what tracks these voice interfaces are struggling with. Once we have all of those, we go to Crowdflower, and we ask a bunch of crowd workers to pronounce these tracks. We take all those transcriptions, we take all those pronunciations, we transcribe them, and now we have a set of text. And so we look at the text, and we figure out which one is the most frequent. How is the voice interface transcribing this song title when people are trying to pronounce it? So we take the most frequent transcription, and then we tag it to the correct track. So we create an alias for the track. So even though the voice interface wants to transcribe OO here as OOH, we can associate that with the correct track, OUU. And so the big question is, does this work? And the answer is pretty resoundingly yes. So on the x-axis here, we have the day. On the y-axis, we have a % improvement over baseline. And this is the track, Where Are You Now, with Justin Bieber. The black line in the middle is when we implemented the alias. So you can see it went up to over 2,500% after we implemented the alias. It improved quite a bit. Other tracks experienced really similar growth. And overall, our alias tracks significantly outperformed the control groups that we held out. And we modeled this as a mixed effects Poisson regression because we're dealing with count data and dealing with a lot of interesting issues there. What we found actually also that was kind of interesting was the control group improved on its own. While our group improved significantly over it, the control group also improved. And this is because, of course, these third-party ASRs are constantly incorporating more and more data and improving, albeit slower, but still improving. But what we found is that this actually isn't quick enough for a lot of our needs. And so we needed a process like this to start tagging all the tracks to make them accessible and to make it a more equitable content space. So in conclusion, we've seen that voice interfaces do disadvantage specific types of content. And this seems to be based on specific sociolinguistic practices associated with different communities of music. We can detect and we can correct this disadvantaged content even though we don't have access to the voice model itself. And we think that these problems are really the first sign of difficulties that we'll encounter as more and more applications make themselves available through voice and through direct manipulation interfaces at the same time. Our hope is that we can find more creative solutions like this to make sure that all the applications we're creating in the future are created equally and equitably for everyone. Thank you.
We have plenty of time for questions.
I don't know whether you would count this as access to the voice model, but what about just taking the 10 or 20 best transcriptions from a speech recognizer and rescoring them? A lot of the APIs will give you access to those. They're called word lattices or character lattices.
So I think the specific one we were using, at least in the way that it was set up on this prototype, I wasn't seeing that we had access to that. But I think that we're kind of, approximating the same thing by having multiple people say it and then having the first transcription from that. But yeah, essentially, sorry, were you going to say something?
Well, I was also wondering about the crowdsource-based OOV, out-of-vocabulary pronunciation models that are out there. I mean,
yeah,
the speech community have worked on this too.
Yeah, definitely. And so I'm not sure how we would integrate those into a third-party API, I guess was the difficulty that we were having there. But it seems like a lot of these issues can't really be solved just simply by even a perfect vocabulary.
Yeah, I mean, the purpose of out-of-vocabulary models is to handle the words that aren't in the vocabulary. It wouldn't be for a perfect vocabulary.
Yeah, but I'm saying it's kind of a substitute for that, essentially. Or you're talking about like pronunciation models.
Well, yeah. I mean, I think there is a fair amount of work out there in the speech community that really wouldn't have been that hard to reintegrate into this.
Yes. Thank you.
Hi, I'm Haven from Sony Electronics, and I was wondering if you think the similar approach can be used to kind of in a reverse way. So I'm specifically thinking about like screen readers for blind people, and then they also have the problem of not reading these type of names correctly. And then do you think this can also help them?
Yeah, I think that this is a pretty like generalizable process that you could apply to something like that to see, you know, how, I guess in this instance, we're talking about how people are understanding what the screen reader is saying aloud and kind of see where those disparities are. Yeah, I think that the whole kind of detection method is pretty robust and could be applied to that arena. And yeah, I'd be curious to talk about that a little more.
Okay, thank you.
Yeah.
Hi, Rena Webby from University of Waterloo. Great talk. My question is, can you explain a little bit more on how you dealt with like anglicized versions of names in other languages?
Sorry, can you say that in part of that question again?
So how did you deal with anglicized versions of titles or names in other languages? So if it was originally in Spanish, but we find that this is primarily going to be English-speaking people on Crowdflower, or did you look for people that spoke the language, or how do you deal with that difference?
Yeah, so I talk about this a little bit more in the paper. And while the non-English languages were one of the most frequent categories that we dealt with, we actually excluded those from a lot of the crowdsourcing stuff because of the exact issues that you were talking about there. We didn't want to, you know, encode incorrect pronunciations into the system that we were using.
Let's move to our next speaker.